Here's an extended problem about probability with calculus, specifically working with continuous random variables. It's to explicate a lot of the ideas in section 8.5 of Stewart, which is just a basic intro to how to use calculus in probability. So here's a little bit of a contrived example. It's a waiting time example, but it's not using the exponential distribution, the exponential probability density function, which it has really nice properties. It's just using a sine function. So suppose that the time for my munch pudding to come out of the kitchen, I'm waiting for my munch pudding, and from time 0 I start the clock, and I've observed that every day I wait for this, and the probability distribution of when I get the pudding has a probability density function of the form that's a sine function from 0 to pi over 2 and 0 elsewhere. And I've put a k in here because if it was just sine t, it's very unlikely that this would have one of the key defining properties of a probability density function. Remember, the two key features are that this has to be a positive function, and indeed, if t is between 0 and pi over 2, this is going to be positive as long as k is positive. And the integral has to be 1, because the integral of the entire probability density function is the probability that something happens, and that always has to be 1. So the first thing in a lot of these problems is, let's find the k. Okay? For some reason, a sine function seems to be the right model. It's a bit weird, but that's what b is going to be about. And let's find the k. Okay, so we just need that the integral of the function is equal to 1. Now that's the integral on the whole real line. So that's minus infinity to infinity. Okay, and so usually or often that's going to be an improper integral, but with a lot of these functions, there's going to have this piecewise definition. It's supported on a finite interval. So supported means the place where it's not 0, and everywhere else it's 0. What all that does is it does something very simple. Piecewise functions usually are a pain in the butt in calculus, but for integrals, and for particularly this kind of piecewise function that's 0 on everything else but an interval, it just means that the integral is going to collapse to the integral from pi over 2 of k sine t. And that's not too hard. Okay, that's supposed to equal 1. So k times, okay, and then that's just going to be cosine t, or sorry, minus cosine t, from, let's see, from 0 to pi over 2 is equal to 1. And cosine of pi over 2 is 0, and minus cosine of 0, but it's with a negative because it's at the bottom, it's just going to be 1. And so, in fact, k turns out to be 1. So it's a pretty special case that, in fact, we don't need a k. If we had accidentally put the sine t in here, it would have worked. That's almost never true. It just happens to be a very simple function. Okay, so from now on, we know that f of t equals sine t. Well, let's actually do the real definition. It's this piecewise function, but I just don't need the k. Okay, that is an honest probability density function, not portable document format as of like Adobe. Okay, so what does this density function say? Okay, well, let's graph it. We know what the sine function looks like, but might as well just stare at a computer graph here. Okay, first of all, this is not really the function. We certainly wouldn't want it to ever be negative. So we're just going to go from 0 to pi over 2, which is about 1.57. Okay, so there's our probability density function. So what does this say about when I'm likely to get my pudding? In particular, is it more likely to get it early, or do I usually have to wait close to the maximum waiting time, which is pi over 2? Because remember, the probability of getting it any other time after pi over 2 is 0. So at some point between 0 and pi over 2, I do get the pudding. Okay, so the probability density function is lower here, and so that means that it's particularly unlikely that I'm going to get it very soon. Now, I could get it very, very quickly, because this is not 0 right at the start, but it's more likely that I'm going to get it over here. Remember, the way the probability density function works is I look the probability that it's in some interval, like between 1 and 1.2, I would create vertical bars here, which is kind of hard to do on Workplace, unfortunately, and here, and I just look at the area under that. If I do that for the same interval of time, like 0 to 0.2, that's the same amount of time as 1 to 1.2, it's going to have a lot smaller area, and so it's going to be lower probability. So when this function is higher, it means things are more likely. Okay, but there's something important that I want to get at, and that's what C is about. what is the probability that the waiting time is exactly equal to pi over 4, halfway in between here? Okay, so you might think, oh, that's what this graph is giving me, right? It's 0.7, and the answer, and that's absolutely no. This is equal to 0, because I said, what's the probability that with infinite precision, infinite number of decimal places, the waiting time is exactly pi over 4? That's equal to 0. This is a continuous probability distribution, and so the probability that any particular time happens is exactly 0. That's a little counterintuitive. Well, wait, but I could do that for any number, and they're all 0. How do they add up? Well, the fact is that that's a very subtle thing. If you insist on infinite precision, you get 0 probability. If you just give this a tiny little bit of wiggle room, you'll get a finite probability. So that's what D and E are about. Okay. So remember, this is not a curve that gives you probabilities. In particular, it happens to be that this guy is always less than 1, but the probability density function can very easily go bigger than 1 because it's not really a probability calculator. The height of it does not calculate probabilities. The area is what calculates probabilities. So, for example, the probability that t is greater than or equal to pi over 4, that is perfectly well defined. It's the integral from pi over 4. In principle, it would be all the way to infinity, but again, this function dies after pi over 2. So it's just pi over 4 to pi over 2 of k sine t. What we figured out that k was just equal to 1. Okay, and that's not too hard. It's just it just turns out to be again minus cosine t from pi over 4 to pi over 2, and so that's going to be 0 and then minus a minus, so plus cosine of pi over 4 root 2 over 2. Okay, which is about 0.707. Let's see if that fits with what we said before, that it's more likely to get it towards the end. You have to wait more than half the time. Yeah, the probability that I'm going to have to wait more than half the full waiting time is about 71%. That's definitely more than half. Okay, so that's the simple kind of question that the probability density function does actually answer, but you have to do an integral to answer that question. Now let's look at this. Let's look at the probability that I'm really near, that the waiting time is really near pi over 4. That's very different from this, which is kind of a meaningless question, and the only actual accurate answer is 0. What is the probability that, to a certain precision, plus or minus 0.01, the waiting time is equal to pi over 4? Okay, that is something I could do. I could get an exact answer by doing an integral just like I did here, from pi over 4 minus 0.01 to pi over 4 plus 0.01. But notice I said approximate. And I want to get at the issue of, okay, what does the probability density function actually measure? Is it this weird thing that I can't really interpret directly and I always have to integrate it? Not really, okay. Because if I'm going to approximate that, well, that's the area under this curve near pi over 4. It's right in the middle, okay, with a width of 2 times 0.01. And because this curve isn't drastically changing in that small region, I could approximate it by a horizontal line. This is basically doing the rectangle method, a small sliver of the rectangle method. So I'm basically drawing a little rectangle right around pi over 4, and with a very small width. Okay, so this is approximately equal to. Let me just copy it here. This guy is approximately equal to the height times the width, and the height is f of pi over 4. Okay, and the width is just 0.02. Okay, so that is one way to interpret the probability density function, is that it gives you an easy way to calculate the probability that your random variable is near a certain value with a certain wiggle room. And it gives you an approximate answer for that. And that, of course, well, that's sine pi over 4. Happens to be root 2 over 2 again. Oops. Totally wrong thing. Times 0.02. Okay. Which is approximately equal to... let's just do that numerically. Okay. Oops. Let me put another approximately here. And that's approximately equal to 0.014. Okay. So about 1.4% of the time, I'm going to be in this small region of time. Now, that's a pretty small number. Does that mean it's unlikely to be near pi over 4? Well, it's a small number mainly because I just had a small wiggle room. The smaller this width is going to be, the smaller the probability. If I say, what's the probability that it's within 0.00001 of pi over 4, I'm going to get a small number. Okay. So what the probability density function is really doing is it's saying, given that this number is pretty small, how small is the probability going to be? And it's really, that's what the probability density function is giving us. It's the multiplier that when you multiply it by the width, the wiggle room you have in your variable that you give it, it gives you the probability to be in that region. So in other words, another way to say this is that f of pi over 4 is approximately equal to that probability divided by the length of the wiggle room. And that's really a good interpretation of the probability density. It's why it's called a probability density. It's saying take the probability divided by how much wiggle room you allowed. So in that wiggle room, how dense is the probability concentrated? How densely is it concentrated? Okay. So that's mainly why I asked that. You don't see this maybe too much in the book. It's really a conceptual question. It's really getting towards the interpretation of what does this curve mean. It says that if this is low, then I give you a little wiggle room. I'm going to have a tiny probability. If this is high, if I give you a little wiggle room, it's going to be still a small probability, but that much bigger than it was over here for the same given amount of wiggle room. Okay. Or margin of error, to be more precise, maybe. Oh, you find the mean waiting time. All right, so the mean, okay, is great in terms of the picture here. There's a very nice analogy between the mean and the center of mass. Okay, so they talk about that in the book, that it's exactly the same calculation as the center of mass if this really were an honest-to-God density. If this were like a log and the density was really small over here and it was really dense over here, it turns out that the mean calculation, I'm not going to go into the details to save time, is exactly the same as the center of mass of the log. And with one additional feature, is that because it's a probability density, the integral of the density itself is always supposed to be equal to 1. That's the analog of the mass. So one of the annoying things about a center of mass calculation is you usually have to divide by the mass. Well, guess what? We don't have to do that here because it's always equal to 1. So what's that center of mass calculation? You look at the density, but then you multiply it by, you look at each piece of the probability distribution, and like right around 1, I want to multiply how likely is it to have a probability near 1 times the value 1. Over here, I'm going to multiply how likely is it to have the probability near 1.5 times 1.5. Okay. And so you get the integral of t sine t. Alrighty. Now, how do we do that? Oh, that's a parts calculation. Okay. So let me break this up into 2 videos because I don't want to make them too incredibly long. But that's going to be a parts calculation, and then we'll do some other ones that are also a little interesting in G and H.